And we can sort of look at the MOSFETs here to figure out the signal swings. And I should have mentioned earlier, actually, with regards to this point, this is actually not VDD because it's going to be constrained by the signal swing of each level of MOSFETs. So, right, because I mentioned the whole point of the biasing is to keep everything in saturation for that amplifier behavior. So each of these, when this VDD is going down here, each of these MOSFETs is going to want to take some because it needs to stay in saturation. And the signal swing of each transistor is the minimum, or sorry, I get the signal swing in total is the maximum output voltage range, right, which is used for our differential output. But each voltage will have a certain amount that is being subtracted from VDD that's going to reduce our signal swing. And for this transistor, this MOSFET to stay in saturation based on this the equation models we have, we need VD sat to be less than or equal to the drain source voltage. So that means that, and the same goes for this guy, right? And then that's before reaching the output here. And that means that at minimum, this M6 needs whatever VD-sat is. It's going to be subtracted from VDD to affect the signal swing. And what I mean to say in general is that the output common mode voltage is going to be equal to VDD minus the VD-sat of both of the transistors above it, right? And then the transistor below it will affect the minimum of, oh yeah, sorry, this should be maximum um, common output voltage, and then there's also a minimum, and instead of these two transistors, it'll be this one, but the equation will be very similar, essentially. And signal swing is so important because that's going to determine uh, how large the output is, which is going to, of course, our gain is equal to the output divided by the input, so it's going to proportionally determine how large our gain is as well, which, of course, is very important in the function of the circuit.